Yeah. Yeah. So I think we have done a little bit of information theory. At least we are aware of the basic concepts, basic definitions about information theory. And now we'll start talking about, so start talking about how these definitions, okay, can be applied to understand the exchange of information or information processing in using a channel. Okay. So yeah, so we'll start doing that. So basically, when we started this course, okay, I talked about a model of a digital communication system. In fact, I gave you a block diagram of a communication system. So where you had this, well, I said actually it is a point-to-point communication system. So where we have a source, where we have a source, and we have a destination, and in between source and destination, there are some blocks. So like encoder, and then there is channel, and then there is a decoder, and there is destination. And in this channel, this is a noisy channel. So there is noise. Okay, so I must tell you that when we talk about the mathematical theory, okay, so mathematical theory means it deals with like mathematical models. So we do not have physical sources or physical channels here in this case, for example. So what we do is, um, so there is something, let's say, which is physical, which can be implemented using physical devices. But when we study in a classroom situation like this, so we study only of the models which can be mathematically tractable, let's say. Okay, so we only study mathematically tractable models. Okay, so these are not, I would say, I mean, this is just a block diagram. Okay, this is not a real communication system. Okay, it is just a block diagram. Okay, there are some parts, and maybe there are a lot of things in between which we are not giving in discussing in details, let's say. Okay, so this is just a mathematical model, you can say, of the communication system, and we'll only be studying mathematical theories of exchange of information between the source and destination. Okay, and most of the cases we'll be studying simple, or let's say simplest classes of mathematical models of different kind of sources and different kind of channels. Okay, and once we understand that, okay, based on that understanding, we can possibly study, complicated classes or models, or in a
Sir,
situation where we have
your screen is not visible.
oh, just a minute. What happened? Why? Just a minute. Okay, so yeah, so we have a source and we have a destination, and in between we have three blocks, let's say encoder, and then channel, and then decoder, because you want to encode your information, which will be transmitted, and it will go via a channel, and then once it is reached, so there will be a decoder which will decode information, and then it will be then it will reach the destination, let's say. Okay. So now the question is, this is just so this is where we started with. So this is the block diagram. Okay. So this is the block diagram. Block diagram of a communication system, let's say. Now, if we go into if you go a little bit further in depth, okay, then we'll see that it can be, it can be represented in a much more, I would say, much more close to reality. Let's say, or I can include some more blocks to understand what is happening. So let's say we'll talk about source, and then you have source encoder, and then this is a binary data, and then we can have a channel encoder, and then we have a channel, and this channel is actually noisy, so there will be a noise, and then there will be a channel decoder, and then it will decode some binary data. Then this will be source decoder, and then we'll say that it has reached the destination. So, here we have included one more block. Let's say we said it is channel encoder and source encoder. Instead of just saying it is just an encoder. Okay, source encoder and channel encoder. And the purpose of the source encoder is just to represent the source output. Okay, so whatever the source is. Okay, so maybe some letters or alphabets. Okay, so the job of the source encoder is to represent the source output by a sequence of, let's say, binary digits. Okay, it need not be binary digits, but using the way we want to encode it. Let's say we want to encode it using strings of 0 1s, then it is just binary digits like bits. Okay, and then this sequence of binary digits will be supplied to a channel encoder, and then it will go through a channel, then it will reach to the channel decoder, and it will decode them again, whatever form it is received. Let's say it is a waveform, and from there, this waveform, then again it will generate the binary data, and then it will encode into the binary data will be again decoded, and then it will reach to the destination. Okay, so this is the idea here. So this job of the source encoder is to encode the message or the information, okay, using some binary digits. Okay, now in this kind of a situation, let's say in this kind of a system, what is our primary concern? Okay, one concern could be here. Okay, so one primary concern could be in this step itself, source encoder. Now when I'm saying it will encode my information, it could be some alphabet, letter, whatever you want to send. Okay, whatever it is, a video, audio, anything. Okay, in any kind of communication system, whatever you can imagine. Okay, the question is for an encoder, okay, that how do you encode, okay, the information? Or let's say the example we had started with, it's like, let's say we have some alphabets, okay, some letters, English letters, let's say. Then the question is who and how, let's say, or let's say who is clear, let's say encoder, how will it decide? hmm, How will it decide the binary digits corresponding to each of these alphabets. Okay. Now the second point is once it is decided, let's say some alphabet, okay, it is decided, let's say for A, B, C, D, X, Y, Z, all these alphabets, suppose somehow it is decided. Somehow it is decided. We'll talk about it, how to decide. But let's say somehow it is decided. Then there is another problem. The problem is here. Now suppose, so what is going on here? The binary data is being supplied to the channel encoder. Now the question is per unit time, let's say per nanosecond or per second, whatever it is, unit is. So let's say per unit time, okay, whenever how many such binary digits should be supplied to the channel encoder? How many binary digits per unit, okay, will be passed on to the channel encoder? Not only that, suppose it is so there is again a question that there are two questions here. One is how to encode means given a letter, for example, in our previous example, given a letter, an alphabet. First of all, we need to decide the length of the sequence or the length of the string of zero ones for each letter, for each sample point, A1, A2, AK, whatever it is, let's say. Second thing is once it is transmitted to or it is being sent to a channel encoder, the question is per unit time, how many such binary digits will be sent? Okay, so these are the real issues here. Okay, and next question is when it, so this is about the encoding side. Next, when this particular data or let's say the sequence of binary data, okay, it has to be reliably sent through this noisy channel. Now, once it reached to the decoder, now the job of the decoder is again very crucial because it has to decode the same binary sequence or binary data sequence which you are transmitted. Okay, even if there is a noise. Okay, there is a noise means due to the noise, once you are transmitting a string of zero ones, some zeros can be flipped to one or some ones can be flipped to zero due to some noise. Okay, then the channel decoder, it has to create a binary data to the source decoder, the let's say with high probability the original binary data sequence. So this is also a major question. And second thing is once it is done, then the source decoder has to decode whatever is being sent. Okay, suppose the destination, the receiver, okay, he knows how it is, the coding scheme, let's say, then it will just decode what is being sent or what is being received. Okay, so this is the receiver and this is the sender, let's say. Okay, so there are a few questions here. Okay, so and now we'll gradually try to understand how this can be done. I mean, in a communication channel like this, a system like this, how first of all encoding, what is the encoding scheme? Second is one per unit time. Okay, how many digits to be transmitted to the channel encoder? And second thing is how one can even if you are transmitting this waveform, let's say, through a noisy channel, how one can retrieve the original binary sequence. So without any error, let's say, or with high probability, okay, or minimizing the error, let's say, okay, with high probability, channel decoder should decode, let's say, the original binary data, and it will send to the source decoder. Okay, so there are many things here. Okay, so now gradually we'll start talking about all this. Okay, so first of all, we need to fix the some source information, let's say, and for that we'll assume that. So as we said, that Shannon said, okay, the source is not information source is nothing but a random variable. So we'll assume it like this way. So whenever we are saying random variables, so there are some possible inputs. Let's say we'll call them, let's say, alphabets. Okay, and we'll call it, let's say, A1, A2, AK. So they, let's say, okay, so let a1 a2 dot ak be the source letters, okay, which you want to transmit with the source letters, okay, which the source produces, let's say. And then the question will be how information theory can play a role into this communication system. Okay, so A1, A2, AK. I mean, information theory means whatever we have developed all these concepts. Let's all these definitions, and those are all also those are only very basic things. We'll develop few more things, but before that, let me give you a flavor of the context. Okay, context of the coding where this information theory will play a big role. Okay, so let us say this source produces this letters. So let's say A1, A2, AK, and these are produced. Okay, so for example, let's say, I mean, for the sake of an example, you can assume that this A1, A2, AK could be all the English alphabets. For example, A, B, C, do up to Z. Now, suppose the sender wants to send let's say a bunch of letters, so maybe some word, okay, and word, let's say. So whenever the sender wants to send an word, so it is a sequence, okay, of these alphabets A1, A2, AK, where it will be A, B, C up to Z, okay. So, and we say that all these letters do not appear randomly, but they come with a probability because we are assuming that information source is a random variable. So we assume that let let let's say P of A1, P of A2, P of AK, okay, be the probabilities of each of this possible outcome of each of these possible outcomes, okay. And let us also assume that, I mean, here, so that's why I was saying in the beginning that we will study only very simplest mathematical models, okay? Because of many reasons. We'll go to the so in the beginning, let's say, we'll only study very simplest mathematical models. Now here I'll make a very big assumption now. So the present models, and let's say this letters, the appearance of these letters are independent to each other, okay? And these letters, meaning, are independent, which is not a good assumption. Independent in a sense, suppose I'm constructing a word, okay, English word. So if I just start, let's say, I start with something, let's say Z, I start with Z. And then I cannot say my next letter will be any letter, okay, from A to Z. I cannot say that because that may not give me a word, okay. So if there are only a few words, okay, whose first letter starts with Z. So the next letter, it cannot be independent of the letter Z. So any word is not just bunch of some random, let's say, letters. Okay, any word is not a bunch of random letters. Okay, so there are many things. Okay, so for example, if you pick the English dictionary, so pick any word. Okay, it is not like putting some random letters together. Okay, so they do not, so they are not statistically independent. This is what I'm trying to say, that these letters, they are not statistically independent, okay? But here, for the case of our model, let us assume that they are all independent, okay? So they are all these letters, let's say they are independent. And we'll also, another assumption we will make, which is also a not close to reality, let's say, we'll make another assumption, so which we'll call like the source. Okay, so this is actually, this is the assumption. So this is what is called the, okay, yeah. So which means which we call call as memoryless memoryless sources. Memoryless source. Okay, this is a memoryless source. Memoryless source means whatever, okay, the letter we choose next time, it is independent of the letter we chose earlier. Okay, so this is independent of that. So this is not very realistic, but we'll assume for the time being, we'll assume that it is the case. Okay. Okay. So I may give you an example. I don't know. Maybe probably you know this. I mean, if you watch Hollywood movies, so in many movies you'll find it like they use the word Morse code. Okay, Morse code. Before defining what is the code, I'm just saying the Morse code. Or if you just type it in Google and just uh, click on the Wikipedia page of Morse AC, I think Morse code. If you just click on the Wikipedia page, so you'll know many things about Morse code. So Morse code is like, okay, you have a, so actually Morse, his name is I think Samuel Morse. He was like a scientist who first invented the telegraph. You know, telegraph means it is a, you can assume that the telegraph is the first kind of a telecommunication system. Okay, long back, I think it was around 1800 something, 1820 or 30, something like that. So he is the, yeah, he discovered this. So he used his coding scheme to code all the English alphabets and the numbers like 1 to 0. And for example, he used basically two kinds of um, letters for, so these are not binary digits, so it is like one dot and one dash. Okay, so using this dot and dash, he produced a coding scheme for all the English alphabets, okay, A to Z, and for the numbers. Okay, and what he decided is, I mean, his coding scheme like the Morse code. So these commonly occur letters, okay, like I said earlier also. Okay, so he used to give very small code word. Okay, code word means a bunch of these symbols like dot and the dash. Okay, so for example, yeah, so you can just you can see this, visit this Wikipedia page, you will see. Okay, but the point here, what I'm trying to tell you here is, like here I said, now when I said this, we have to encode this source letters in terms of, let's say, 0 1s. In terms of 0 1, for example, in Morse code, it's not 0 and this is dot and dash. So then the question is, should we pick a fixed length? I mean, a string of 0 1s or binary string of fixed length for all the letters, or should we vary it? That is also a question. Okay. For example, in Morse code, he used small length code word for commonly occurring letters. Okay. A large length code word for 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 the letters which do not occur uh, or do not occur commonly, let's say, or occur less. Okay, for those letters. Okay, so he used small length code word. So first of all, now I'll define what is a code, what is a code word. Okay, so let me just give you the definition. So the definition is, okay, a source code or just a code. Okay, so you are see, a source code. Let's just see. Most of the cases we will write it using C. We'll use the letter C, capital C, for the code for a random variable. A random variable X is a mapping from the corresponding alphabet, or you can say sample points from a star. Let me precisely write like the range of x. Precisely, I mean this x, this alphabet, I mean this set consists of all the numbers corresponding to all the sample points. Okay, because it is a random variable. Okay, the range of x to uh, to d star. Let's say I'll tell you what is d. The the finite the finite length string of symbols from a, I think you can say d array alphabet. Okay, what do I mean by this? I'm telling you. So C is basically from x to 0, 1 up to t minus 1. It is nothing, which is t star. Okay, so what I'm trying to tell you here is, like I said, binary digits. Okay, you want to code each of the sample points or the inputs, let's say, using 0 ones, right? The binary digits. It need not be the 0 1. It could be 0 1 2, 0 1 3, 0 1 4, and so on. Whatever you want to do it. Okay, you can do it. So in general, this is the definition. For example, in Morse case, in Morse code, so this D is equal to like dot and dash. Okay, this is what is D, or you can say D star. Okay, so this star, this symbol is due to this Thomas and Thomas book, so they use this symbol. So that's why I'm using this symbol. Otherwise, you can also call just D is some set of symbols which you want to use for your coding scheme, for your code word, let's say. Now, what is a code word? The code word means meaning the C of X. So once you pick a particular X from this X, okay, then this is called a code word. So basically, a code is a set of code words, code word corresponding to X. And I'll denote this L of X, this as the length of Cx. Now I think all the notations are here. So Lx is what? The length of Cs, which is the code word for X. Okay. So now here, if you look at my example of this communication system, the diagram here, the question I raised is the following. If we have this A1, A2, AK, then I have to decide a coding scheme for all these letters, A1, A2, AK. So that means here the questions that I raised that can be now defined using symbols. So how to decide? How to decide? This is the first question. It is how to decide C of AI. That's in the code word of AI, and L of AI. That means what should be the length of this code word? Okay, these two things now we need to fix. Now, as I said in the Morse code, because it is very popular, it doesn't need any mathematics to understand the code. So if you just look at the Morse code, you will see that small length code words were used, okay, for commonly occurring letters, okay, and which are not commonly occurring for other letters, okay. He used uh, code words of bigger length, okay. So that means he used variable length codes. Okay, so the length of the code words, okay, that is not fixed. That is varying with the letter. Okay, so those kind of codings or those kind of codes, or the code words are called. So there are two kinds of code words, I could say. So code words can be different two kinds corresponding to a coding scheme. It is a variable length code words, and just I can say variable length, and this is the fixed length. Okay, fixed length means for all the letters, the length is fixed. Length of each code word is the same. Okay, so this is fixed length. Fixed length. Okay, now apparently it may not seem like this is a very big deal. Okay, but it is actually a very big deal. I'll tell you why. I mean, I'll tell you why means I'll just give you an example where can it make a difference. Okay. Now, see, my next problem was this one, that you need to transmit these code words through some channel. Okay. Now, per unit time, okay, how many, let's say, per unit time, how many code words, how many, let's say, symbols, let's say, how many symbols of like zero ones, if you encode it using zero ones, how many symbols, or maybe something else, like in the Morse code it is like dot and dash. So how many symbol you can transmit per unit time? So if you have a variable length code, then there is a problem. The problem is, suppose you can transmit, let's say, 5 symbols per unit time, but you have a code word whose length is 6, then the entire code word cannot be sent at, together, let's say, at the same time. So there will be a waiting list that the next time it will be sent. So there is a practical problem here. On the other hand, okay, if you have a fixed length code, meaning all the code words, they are of fixed length, and then possibly you can have a scheme where per unit time, let's say, you will be sending those many symbols, which is your code length. So in that case, it is not of very problematic thing, I would say. It is very easier compared to the other one. Okay, when you do not have fixed length but a variable length codes. Okay, or variable length code words. Okay, I mean, if you know about
Uh,
teletype.
so can you please repeat this? Like, what is the problem with the both of the cases?
Yeah, so the thing is, when you are sending this per unit time, you have to send this. Okay, this binary data per unit time, you have to send this. The question is, per unit time, how many symbols or how many, let's say, bits? I mean, suppose we are doing binary, okay, binary digits. So how many bits per second, let's say, you can transmit through this channel encoder or through the channel? Suppose there is a limit that per second you can only transmit 5 bits of data. Now, suppose there is a code word whose length is, let's say, 6 bits. Okay, and 6 bits means 6 binary digits. So then you cannot transmit the entire code word at a particular time. There has to be a waiting time. Suppose that letter is, let's say, some X. Okay, then whenever you want to send X, you cannot set all the symbols, all the digits, okay, all the bits together. But five of the bits you have to send, and for the other one, the remaining one, you have to set it at the next time. Okay, okay, maybe I can give you an example of a coding. Let's say, suppose, okay, I mean, I didn't give you an example of a coding. So let's say, okay, so I mean, by coding, what I mean, let's say, mm, okay, let's say, I mean, let's say, A1, A2, A3, A4. Okay, these are my alphabets which I want to send. Okay, ABCD. I mean, a combination of this. Okay, I want to send. Then what I can, I could an example of coding scheme could be like this. Okay, let's say coding scheme one. Let's say coding coding scheme one is like, okay, so let's say A1, A2, A3, and A4. And let's say my coding scheme one, I want to encode A1 as 00, and to encode A2 as 01, and to encode A3 as 10, and to encode A4 as 11. This is one possibility. You can suppose you think like, no, you don't want to do that. Okay, so you can have another mode of doing it. Let's say it is 0, A1 is 0, let's say A2 is, let's say 10, A3 is, let's say 110, and A4, let's say 111. You want, let's say, like this way. You suppose you design it like this way. Okay, then the question is, this is the difference about this scheme and this scheme is this is a fixed length. Okay, this is fixed length, and this is varying length, or variable length code. Okay, so now the thing is, when you are transmitting, suppose you are sending a bunch of letters, let's say A1, A2, A4, A3. This is what you are sending. Okay, there are some letters. Okay, I mean, suppose you have a message which consists of only 4 letters. Okay, and they have some probability distribution, this and that, or everything is there. But let's say this is my coding scheme. Okay, one's coding scheme is by fixed length, another is by variable length. Now I can have a mechanism that through my channel, I can send 4 bits of data per unit time per second, let's say, or maybe 2 bits of data per unit second. Okay, per second, let's say. Then if I can send 2 bits of data, then I can send A1, A2, A3, A4, one by one, whatever, based on, I'll first send, let's say A1, then A2, and then A4, and then A3. I'll send it this way. So I'll send first, let's say 00, then I'll send 01, then I'll send 11, and then I'll send A3. Okay, 10. But for the case of variable, then the problem is, even if I want to send A1, I can easily send it. A2, I can send it. But whenever I want to send A4, since the problem is that per unit time per second, I can only send 2 bits of data. So I cannot send 111 altogether. So I can send only 1 and 1, and then I have to wait. I have to have some waiting time. Next time again, I'll send 1. So there is a problem of synchronization, or there is a problem of time. So if you have a variable length, there can be a problem of time. That is what I'm trying to tell you. Okay, so I mean, this can be variable length or fixed length, but there mathematically, apparently, it may seem like, okay, there is no problem. I can code it using this or that. Okay, but practically, there may be a problem. Okay, so just to bring this point out, I gave you this example that there can be some, I mean, this can have some practical significance, whether you are going for fixed length or you are going for variable length coding scheme. Did you get it?
Yes, sir.
Okay. Now let's say, let
Sir,
us first, yes.
uh, uh, like you said that we will have to wait for some time for sending the next one bit in case of A3 and A4. But then, like, what will be the problem in that case? Like at the end, we are getting the same thing, no? At the receiver end.
No, yes, but you have to maintain a waiting time, and that can be crucial.
Okay.
Suppose, for example, I'm telling you, for example, suppose first time you send, I mean, I am giving you a hypothetical situation. For example, first time, let's say
Okay.
you send these 2 bits, 1, 1, and next time when you are sending this one, okay, it flipped to 0 due to some error. Or maybe when you are sending the first 1, 1, okay, you got, let's say 1, 0, and second time when you are getting, I mean, due to some noise, second time you are sending 1. So instead of this, you may get this one. I mean, this can also happen when you're sending it together, transmitting this together. I mean, all together 1, 1, 1. That can also happen. That it may get changed. It may change to 1, 1, 0 due to the error. That may also happen. But I'm just giving you a hypothetical situation that you need time. Okay, you have to spend a lot of time. So now, if I'm sending 1,000 times, let's say, so I have to then at least, I mean, the number of times it is occurring, that many seconds, let's say, the unit time, let's say, whatever the unit is, let's say it is seconds. So that many seconds I have to wait. That could be a serious practical issue. Okay, so that's why coding. So this is a problematic thing, but we'll show that this is a very useful thing as well mathematically. So in fact, the Morse code, you see, that was a coding scheme with variable length. Okay, this was not a fixed length coding scheme. Although it can have some practical issues, but this is, I would say, this is what is being done or being implementing in most of the cases in our real world, in our modern world. Okay, but when you have this fixed length, okay, this will more relate to the definition of our self-information, entropy, everything. Like whenever we are using fixed length, then we'll have all the, I mean, there is a deeper significance, I would say, with this particular coding scheme. But before that, I'll give you an interesting operational meaning of entropy using variable length coding. Okay, so I'll show. I'll show that in fixed length coding, okay, there's a deeper connection about the definitions of this self-information, entropy, and other things. I'll also give you an example, operational meaning of entropy using variable length coding, and what does entropy mean actually when you implement this. And I'll also give you that example, give you, somebody said, I think somebody said about this multiplication to addition. That's why log is used. I'll give you a practical example of where it is used and why this is important. Okay, why this is used, that how when it converts, okay, log converts this multiplication into addition, and where this is being useful. So that's why we need a log. Okay, this is one justification, the textbook justification. But yeah, but where it is actually used. So it is used in the communication, not in the definition as such. Yeah, definition also you can see, because ultimately we will use the property of the definition only. But when it comes to the application, then you will see that, okay, this is how it can be thought of. So log was necessary, for example. Okay, so yeah, I'll give you an operational meaning of variable length. But let us say first, okay, so we don't have much time today because we'll also have to discuss about this. Mm, what we'll do about the assignment. Okay, so I was thinking about discussing this. Maybe we can do it next time, next day. But let us say I'll give you an operational meaning of entropy. Operational meaning of entropy. Okay, why this entropy is important. Okay, so I'll raise a very important question, and I'll give you the answer also with an example, but we have to prove it mathematically also, and that cannot be done today, maybe next time. Okay, so let me put it this way. Suppose I have two letters, or maybe four letters, A, B, C, D. Okay, so let my source letters, okay, are like A, B, C, and D. Okay, and there is Alice, okay, who wants to send this to Bob. Okay, so these are my source letter, Alice's source letters, and there is a probability associated with this. So let's say the probabilities are like this: P of A, let's say this is half. Probability of B, let's say 1 by 8. So probability of C, let's say 1 by 4. And probability of D, let's say 1 by 8. Okay. So as I said, suppose we have a channel which does not accept this letters ABCD to be transmitted. So I have to encode it using symbols or bits, let's say here 0, 1. So the question is here, how can Alice encode the information into bits? Okay. So what should be the coding scheme? So let's say what should be the coding scheme for Alice to transmit all these letters. What do you think? So what should be the code words corresponding to these letters? Okay, what should be that one? Let's say what should be that one means my question is, how does Alice decide, okay, the length of each of these code words? And then she has to decide about the code words. See, do not put, so whenever I'm saying this coding scheme, there is another problem which I already told you, that there is a problem of decoding also. You have to, one has to, the sender has to encode the letters in such a way, let's say, such a way that there, I mean, maybe there is a one-one correspondence, like all the code words are different. Or suppose, for example, here, I could have easily said it is 0, 0, and this is also 0, let's say, just 0. Then there is a possibility of mixing up things, possibility of error will increase. So uniquely, you may not be able to decode. Okay, so there is another problem of decoding. Uniquely, we have to decode. I mean, there is, okay, I'll give you an example maybe. But let us say, how does Alice, okay, decide the coding scheme for the letters A, B, C, D? Okay, this is the question. Okay, what should be this? Now, let us assume that Alice decides like this. Let's say A equal to 0, 0, okay, and B equal to 0, 1. Just what I gave the example, 1, 0, and let's say D equal to 1, 1. Okay, so these are, let's say, the code words, okay, for all these letters, whatever she had then. Now, so what is the expected length of the code word? Meaning, so once you are deciding a coding scheme, what are the things you should be interested in? It should be interested in that, interested in the fact that what is my expected length of the code, of the code word. So if we calculate the expected length here, what is that? What is the expected length of the coding scheme? Expected length. What is that? Expected length of a code word. What is that? Here? Yeah, so this is 2 bits. What is the expected length? So it is px times lx, okay? Okay, I did not define it maybe. So where did I define this? Length here and expected length here I can define, okay? Px times lx, okay? This is my expected length all over x, okay? Expected length of code word, okay? So that means what is happening is expected length of the code word is 2 bit, okay? That means I need to send 2 bits of information, okay, per unit time to send a letter, okay? But let's say the channel is costly. So then the question will be, can I have expected length which is less than 2? Is it possible? Can Alice design a coding scheme where this is less than 2 bits? Or a bigger question is, what should be the average code length of a coding scheme so that the minimum length, you cannot go beyond that, you cannot go less than that. That's the minimum number of bits you need, okay, to design your code words. That's the average length, which is minimum. So to answer this question, so that's a bigger question. First, to answer this question, so that's a bigger question, but let us first consider this question. This is a simple coding scheme, okay, and it has average length, or the expected length, which is 2 bits. Now, can Alice design a coding scheme whose average length or the expected length is less than 2 bits? Can she do that? What do you think? Okay, not only that. Okay. So suppose Alice uses this one. Okay, suppose Alice uses this one. Let us say. Okay. Now let's say this is being received. Zero zero one one zero one zero one 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 zero one zero one. How can I do that? 1000. Let's say 0. Now, can anybody tell me if this is what is received? What was the code word? What was the actual information? What was the message? Can you decode it? Now see here, there is a confusion now. Okay, you tell me. Okay, go ahead and tell me. Can anybody tell me what was the message actually? Or is there any scope of confusion here? There can be. I mean, is it? My question is to be very precise. Is it uniquely decodable? I'm just giving an example. You may create your example. Is it uniquely decodable? I mean, uniquely decodable means once this is received by Bob, Bob can uniquely decode what is the sequence of symbols that was sent to him by Alice.
Sir, if we take 2 digit at a time and we can make a pair, and if we decode, then we are getting different code words. Like suppose in starting for 00 we will get A, and 111 we will get D, and if we do, then we will not get any confusion. I think this code we will get different uh, output for the corresponding 2 digit.
Okay. So you are saying okay 00 then 11 then 01 then 01 then 11 then 01 then 01 then 10 then 00 then 10. Right? This is what you were saying, right? So it is like A.
Yes, sir.
Yeah. Then D. 01 means B. 01 means B again. 11 means D. 01 is B. 01 again B. 10. Let's say C. 00 it's A. 10 it's B. So it is uniquely decodable. Okay, so that's not a problem. I mean, I just gave you an example. Is it uniquely decodable? Yes, it is uniquely decodable. Now, let us go back to the original question. Can I create a coding scheme whose expected length will be less than 2 bits? Is it possible at all? If it is possible, then what is the minimum number of bits I require? I cannot just send 0 bits, right? I will have a minimum number of bits which will be required always to design my coding scheme. Okay. So how do I do that? And what is the limit? What should be the minimum number of bits I can have a coding scheme for which I cannot design any other coding scheme for which this expected length will go less than that. Okay. So the bigger question here is, this is the bigger question. give, let me directly ask this question. What is the minimum mini what is the minimum value of expected length of a code word? Okay, among all possible codes. Okay, now see here, in this coding scheme, when it is designed, there is no use of the probability. Meaning what? From this probability distribution, it can easily be seen that occurrence of A is much more than occurrence of B and D. Occurrence of C is more than occurrence of B and D, but less than the occurrence of A. This fact, this useful information, the probability distribution, is not used when this code is designed. Okay, so can I follow the logic of Morse? Morse, what he did for commonly occurring, that means if the probability is more, then I'll use a less length code word or small length code word. If the probability is less, then I will use a greater length, a large length, let's say, bigger length code word. Okay, so that could be one way out to design a code word which has expected length, which is less than 2 bits. Okay, so let me do that. So let me design a code using this code word, a code word for each of these letters using the probabilities. Okay, so A is more likely to happen, okay, compared to B, C, and D, and C is more likely to happen than B and D. So let's say another coding scheme. Now let's say here A, I'll give a very small length code word, which is 0. That's only one letter, only one bit. B, yeah, let's say 110. C, let's say 10, because C is the next. So this probability is 1/4. So I'll use C, I'll use 2 bits. For B, because B is less likely to happen because its probability is 1/8, B and D. So for B, I use, let's say, 3 bits code word 110, and let's say D is equal to 111. Now let us calculate the expected length of this coding scheme. Expected length. See here the difference is this is a fixed length code, okay? And here I introduced a variable length code. So then expected length is what? So expected length will be, probability of A was half. So half into 1, okay? 1 is the length of A plus B probability was 1/8, I think. Yeah, 1/8 times 3, because 3 bits, plus 1/4 times 2 plus 1/8 times 3. Okay, and this value is what? Half plus 3/8 plus. Guys, can you see the screen?
Yes, sir.
Yes,
Okay.
sir.
Okay, so then half plus 3
Sir,
by
7
8.
by 4.
So what is the 7/4? Yeah. 7 by 4. And it is less than 2. It is less than 2 bits. Right? So I can design a code whose average length is less than this, 2 bits. Now, here is an observation. What is the entropy of this random variable? ABCD. ABCD, this is an information source. And A is occurring with probability half, B is occurring with probability 1 by 8, C is occurring with probability 1 by 4, D is 1 by 8. What is the entropy of this random variable? Let us calculate that. What is the entropy? Entropy of the source random variable. For random variable, we just need a probability distribution which is given to us, and which is what? Which is minus half log half minus 1 by 8 log 1 by 8 minus 1 by 4 log 1 by 4.
Sir, screen is not visible.
Screen is not visible. Okay. Just a minute. Is it visible now?
Yes, sir.
Okay. So, and this is also 1 by 8 log 1 by 8. Now, if you do the calculation a little bit, so what do you have? Half log half, okay, is what? What can you write about that? So instead of
Sir,
what can we write? Yeah,
sir, on base 2.
half into 1 because it is 2 to the power minus 1. Yeah, Saurabh, you want to say something?
Sir, we have to calculate on base 2, right?
Yes, yes, yes. Base 2, base 2.
Yes, sir.
So
Again,
yeah, so I'm saying bits, so it's base 2. 3 plus 1 by 4 times 2 plus 1 by 8 times 3. Oh, the same thing which you got here. Okay, so this is 7 by 4. This is, and let me tell you guys, this is not surprising. In fact, entropy is the limit. You cannot have a coding scheme whose expected length is below the entropy. So entropy sets the limit for, I mean, I didn't prove it. Okay, I will prove it. Okay, so what I'm saying is that this expression 7 by 4 bits is not accidental. This and this two are equal. It is not accidental. In fact, we'll show that you cannot have a coding scheme whose average length is below the entropy of the information source. And this is the meaning of, or let's say operational meaning of entropy. So what is the amount of information? We said the average self information, right? That is how we have defined entropy. And entropy, we said, okay, this is the, according to the definition corresponding to mutual information, we defined it as average self information, but we said, okay, it measures the amount of uncertainty which is in the random variable. Okay, and this is where it is used. By amount of uncertainty means if you want to encode, so this is operational meaning. If you want to design a coding scheme for the random variable, then the average length will be equal to the entropy. Okay, this will prove. So, but right now I'm just saying that. So this is not accidental. Okay, so this is the limit actually. You cannot go beyond this. Okay, so this is the limit. Yeah, so this is the operational meaning of entropy, and that's why entropy is very, very useful in the context of communication. Okay, so let me stop here today, and we'll discuss about assignment problems, and we'll continue this. If you have any question, you can ask me. Otherwise, we'll switch on to. You please open the assignment problems.